And now, finally, armed with all of the understanding that we could gear ourselves up with of the general theory of relativity, we're going to try to talk about what might happen to the core of a star that is too massive to be stabilized by neutron degeneracy and collapses completely. And then there, as far as we know, is nothing to stop the collapse, and the star collapses completely. We won't talk much about what happens to the star, but we'll talk about what happens outside the star. The collapse itself is, of course, a very highly turbulent and energetic process, releasing tons of gravitational potential energy and creating a wild and violent and turbulent supernova. There are people who model such things. We will not discuss what they find. We will discuss what's left behind outside the star. And we'll start this a little bit obliquely by talking about our gravitational redshift. Remember, from the principle of equivalence, we found that near Earth, if you shoot light up at height h, you find a gravitational redshift given by gh over c squared. This has to do with the acceleration of gravity being g. We've already played with that game before. And away from Earth, we expect that because the force of gravity is weaker as you move farther away, if you're not near the Earth's surface, we expect gh to be replaced by something like minus gm over r up to a constant. And in fact, you can do the general relativistic calculation, and you find that if you're observing from a great distance from Earth, and way off at infinity, and someone is emitting light a distance r from Earth, so the situation is that here is the Earth, you are sitting a distance r from Earth, emitting a light beam that is traveling off, and this light is being received way far off from Earth, essentially at infinite distance. Then it will be reddened because you're emitting from the ground floor to the top floor, but the amount is not gh, of course. There's the weakening of the gravitational field. The correct relativistic expression is this one. The observed frequency will be the emitted frequency divided by the square root of this ratio. We can use the Newton's approximation to write this as lambda 0 times 1 minus 2 gm over rc squared to the minus a half, and then that's the same as lambda 0 times 1 minus times 2 times minus a half is plus gm over rc squared, and that's the expression I wrote there. And so, to a good approximation, we get exactly what we expected. Here's the gm over r that we expected. This is valid so long as this expression here in the square root is much smaller than 1. This means that r needs to be big. Bigger than what? Well, such that 2gm over rc squared is much less than 1, or r is much bigger than gm over c squared. This is called the Schwarzschild radius, and for Earth, the Schwarzschild radius, plugging in Earth over here, is about 9 millimeters. You're not likely to be broadcasting from less than 9 millimeters from the center of Earth, so I'm not worried about that too much in the case of Earth. But what happens if r is not much bigger than the Schwarzschild radius? Then this redshift factor can become quite significant, and its deviation from the Newton approximation can be big, because the x here is not less than 1. And in fact, when you get near to the Schwarzschild radius for some given mass, what happens is that this denominator vanishes, and the redshift becomes infinite. So, can you even do such a thing? Well, the Schwarzschild radius for Earth is 9 millimeters. You can't get there. You need something where mass is more compactly concentrated. If you take the Schwarzschild radius for any object, you can compute it. It's directly proportional to the mass, and I can compute the Schwarzschild radius for the Sun to be about 3 kilometers. So, the Schwarzschild radius for an object of solar mass is 3 kilometers. The Schwarzschild radius for an object of 10 solar masses is 30 kilometers, and so on. Neutron stars, remember, have a mass of about 1.5 solar masses, and their radii are 10 kilometers, so they're not too far from the Schwarzschild limit. You can get to within 3, maybe 4 Schwarzschild radii of a neutron star. At that point, when light is being emitted from the surface of a neutron star, the gravitational redshift due to GR effects is very significant. So, neutron stars are pretty close to being inside their own Schwarzschild limit. But if you can imagine an object that collapses till it's even denser than a neutron star, then there will be a point in space, a ball around this object, of radius determined by its mass, this Schwarzschild radius. And when you approach that distance from the center of the object, the gravitational redshift diverges. It becomes infinite. What does this mean? This means that if I'm watching from very far away and I'm watching something fall on to this massive, dense object, which I'm going to call a black hole, then when I look at it from afar, I will never see the thing that I'm watching getting there, because remember, gravitational redshift is really time slowing down. As I observe from far away something falling onto a black hole, or a black hole's horizon, this ball around the massive compact object whose radius is the Schwarzschild radius, is called the horizon for reasons that will become apparent. But as something approaches the horizon, if you're observing it from far away, what you're going to observe is that it slows down and never gets there. It basically freezes as it approaches the horizon. Moreover, any light, when I say you see it, you would be seeing it by light. Say the thing is a bright, luminous object. Its light will be redshifted, and the amount of energy per photon, remember, is proportional to the frequency, so decreases with increasing wavelength. There's less energy in a red photon than there is in a blue photon. So the amount of energy this thing is emitting becomes less and less. What you would see is this object slow down and dim, and then it would basically become dark as it approached the horizon, but it would take an infinite amount of time as you see it from far away for something to actually get to the horizon. In particular, since any light coming from the horizon is infinitely redshifted, that means it carries zero energy. No light comes out from this ball of radius, Schwarzschild radius, around whatever this compact massive object is. This is why we call it a black hole, because absolutely no light can leave. There's this region called the horizon. It's a ball of radius, the Schwarzschild radius. Any light from that ball or within it, but from that sphere, no light can emerge. And so, of course, not from the inside. Now, because of the way gravitational redshifts work, light that is falling on to the horizon is blue shifted. So if you happen to be sitting near the horizon, you can look back and light falling on you will be intensely blue shifted, and time will appear to you to be moving faster. So your clock will run slow. You can look back and watch the end of the universe happening behind you as you are sitting near the horizon. It will take mere instants of your time because of this general relativistic redshift. This is what the horizon is. The horizon of a black hole is the point at which the gravitational redshift is infinite. This is why it is that no light comes out. This requires an extremely intense gravitational field. Typically, we observe things from infinity. Notice that when I say you have to be infinite far away, the gravitational redshift will be infinite compared to any finite distance. All the infinity is coming out, and the region where R is very close to Rs. So if you're out at 5 Schwarzschild radii, you will still see someone at the Schwarzschild radius have an infinite redshift. So things slow down. Nothing ever goes through a black hole's horizon. So if you ask what happened to the star as it collapsed, the answer is, I never saw that. And as we see it very far from the star's collapse stopped and froze and dimmed and darkened, and all we see is no more starlight coming from there. We'll see later what the other astronomical signatures are, but we've never actually observed, let alone seen, star collapse into a black hole, for the simple reason that by our clocks it hasn't happened yet. It takes an infinite amount of time. Now, okay, that's looking from far away. What happens if you get more close to a black hole? Then you can see some interesting effects. As you get to within a few Schwarzschild radii, relativistic effects become interesting. So stable orbits exist. You can draw nice stable circular orbits around an object like the sun, and as you get closer to a black hole, relativistic effects become more important. You have to orbit rather fast, and for radii less than 3 times the Schwarzschild radius, no stable orbits exist. There exist circular orbits inside that radius, but they're all unstable. What this implies is that any small perturbation, rather than knocking you into an elliptical orbit, will knock you into an orbit that either falls into the black hole or away from the black hole. So that means that when we're looking at objects orbiting a black hole, none because there's always a perturbation from somewhere, none will be orbiting nearer than 3 Schwarzschild radii from the black hole. Now, if the black hole has the mass of a few solar masses, that's 10 kilometers out. That's not really very impressive. But if the black hole happens to have a mass of 1,000 solar masses, that's 3,000 kilometers will be the closest that anything can orbit. And by that time, maybe you can make some hay of it. Because of the deflection of light, at a radius you can compute of 1.5 times the solar the Schwarzschild radius, you find what's called the photosphere. There, light can actually orbit in a closed circular orbit. Light is deflected by this massive star. It's deflected enough that you can imagine photons running in circles around, at the speed of light, around this massive object. Unfortunately, they don't stay there. That orbit is unstable. But what it means is that by the time you get to within 1.5 Schwarzschild radii, the lensing, the optical effects of the black hole are going to be very extreme, and even farther out, they are quite marked, and we'll see that in a bit. And the other thing, of course, is that so what is the deal? Why is gravity so intense in a black hole? It's got nothing to do with the fact that it collapsed. Gravity is intense for the same reason gravitation of a 1 solar mass neutron star is so intense. It's because you can get so close. It's the gm over r squared becoming huge when m is the solar mass, but r is 10 kilometers. In this case, there is a general relativistic enhancement, and in the neutron star case, by the way. Similarly, the m over r cubed tidal forces become huge because you can get so near to such a large mass. And so tidal forces can become extreme when you get close to a black hole. However, I note that since the closest you're ever going to get is the Schwarzschild radius, and if your size is d, this is our estimate for the tidal acceleration between, say, your head and your feet. You can stick for d, 2 meters if you're a tall person. It's twice g times the mass divided by whatever your distance is cubed. We'll plug in as the distance the Schwarzschild radius. The Schwarzschild radius, remember, Rs is 2gm over c squared. And so plugging r cubed here, we see that 1g and 1m and 1, 2 cancel, leaving us with 4g squared m squared on the denominator and a d times c to the 6th on top. These accelerations can be huge, but the larger, the more massive the black hole, the less extreme the tidal effects are. So a solar mass black hole will completely rip you to shreds if you approach its horizon. A 4 billion solar mass black hole will not. In fact, you might not even notice that you crossed the horizon. We'll talk about that in a second. Okay, so this is what you'd see. A few Schwarzschild radii. I want to go and look at the horizon and beyond it. How can I see beyond the horizon? I thought you can never get there. Well, no. You can never get there as seen by a clock ticking far away here on Earth. But if you were to fall into a black hole, believe me, you would fall in. I never said the star never collapsed. I said we have never seen it. It hasn't happened in our time. This is the weirdness of gravitational redshifts. The star, if you were near the star, you would have been collapsed. The star itself indeed collapsed. And we'll see what happened to it. But we from far away have not seen it. So what we need if we want to study things closer into the black hole is we need to use a better clock. Let's use the clock of an observer that is freely falling in. And then the shape that you see of the vicinity of the black hole is given by this sort of diagram here to the right. And I have to elaborate a little bit on what this diagram means. So this diagonal, this region over here, is the space outside the black hole. And out here, very far away, is where we are. Now, this line over here, this thing over here, and this thing over here, this is the horizon. Now, it's very strange. This is a space-time diagram. This is the radial direction, and this is the time direction. And what you notice, we've ignored the fact that you can go around a black hole. We've pretended only distance from the black hole and time are relevant. And what you notice here is something very strange. The horizon is not a place at all. It is tilted at 45 degrees. The horizon is the position of a light beam when you use suitable coordinates to be able to distinguish that. In the coordinates we got using clocks from far away, we couldn't really tell that because the light cones in those coordinates were squished down to nothing. But in these coordinates where you can see what's going on near the horizon, you see that the horizon is in fact, could be the world line of a light beam, and this immediately explains why light cannot leave. So if you are an observer near the horizon, you can still broadcast a signal, and it will at some point arrive far away, but once you cross the horizon and you're inside, a signal, even traveling at the speed of light, will never get out of the horizon. To get out of the horizon, a signal would have to travel faster than light, and that is why no kind of propulsion will get you out once you cross a black hole's horizon. And this is very strange because we said the horizon was a place, but suddenly it appears to be a light-like thing. It's different places at different times. How did the horizons move with time? This again has to do with the fact that it moves as seen by a clock that is relevant near the horizon. Remember, this clock ticks infinitely slowly as seen from far away. So from far away, the horizon looks like a place. This is a more accurate description. This is why light cannot escape. Over here is the interior. This is where the black hole is. And if you try to relate this description to the description in terms of distance from the black hole, then there's an animation that sort of tries to exemplify this. These lines are lines of constant value of r, the sort of putative distance from the black hole. And far away from the black hole, you see that the constant r surface might look like this. And so this coordinate could be thought of as distance from the black hole. But as you move closer in, lines of closer distance to the black hole look more and more like this. And then the line r equals r Schwarzschild is exactly the horizon. And after that, we see something funky happening. The line, changing r now is no longer a motion in space. Changing r becomes a motion in time. And indeed, this region over here is something called the singularity. Once you are inside, and we'll talk about its significance, once you are inside the black hole, anything you do, even if you move at the speed of light in either direction, you are bound to land on this boundary here. That is your future. So the singularity of a black hole is not a place. It looks from infinity like a place. The singularity at the center of a black hole is in fact a time. It's a when, not a where. It's everybody's future once you enter the black hole. So now, penetrate through the horizon. Note that this is quite possible. You can be an observer here, and there are definitely inertial trajectories that take you through the horizon. What happens when you cross the horizon? Well, once you cross the horizon, here is what happens to you. Once you're inside the horizon, you can make an easy calculation that within a finite proper time, you reach the singularity, that crazy contour at the top of the diagram. What is a singularity? A singularity is a place where the tidal acceleration, remember, this is the actual gravitational effects, go to infinity. And diverges literally becomes infinite. That means that first your feet get ripped off from the rest of you, but then eventually your atoms get ripped apart. Matter gets decomposed by the tidal forces. And then what? As you get even closer to the singularity, well, then things become infinite. And this divergence, this infinity in the calculation, signals a breakdown of the equations. The truth is that I told you at some point that Einstein's theory of relativity was incomplete. This infinity is a signal of its incompleteness. It cannot predict. We do not know. We do not have a theory that predicts what happens when you fall onto the singularity or what happens to the material of the star. Remember, the star, in its own time, receded inside its Schwarzschild radius, and then every bit of the star, in finite proper time, as measured by its clock, crashed into the singularity, and then we don't know, because we don't have an equation that describes it, and hopefully someday we will.